Hi, I'm Samuel Green.
I'm Ernest Green.
This is our final project. In going into this project, our objective was to build a rocket that, regardless of external forces, could be self-stabilizing in an upward trajectory. As well as that, we also wanted a rocket that could be successfully recovered and reused.
So, one of the biggest challenges with computer controlled flight stability in a rocket is knowing the real-time position or tilt of the rocket, the attitude of the rocket. Um, in order to, our solution for this was using an MPU 6050 accelerometer sensor. This communicates with the board using the I2C communication protocol, reading raw data from the chip, from the sensor. We were able to take that and using some C functions, turn that into real-time angles of tilt in the rocket. And using those angles, we were able to implement a PWM communication with servos on control surfaces on the rocket to guide the rocket in an upward trajectory if it were ever able to tilt anywhere that's not straight up.
The next challenge was recovery. And to tackle that, we used an altimeter, also using I2C. We were able to take that data and find when the rocket began its descent. After 3 meters of descent, it would deploy an ejection charge that would release a parachute.
This ejection charge is driven by a cascade of MOSFET transistors, using LiPo batteries to power the ejection charge and the board to drive the MOSFETs.
And in the remainder of this video, we'll be showing how we tackle these objectives of using I2C for both the altimeter and gyroscope to both control the fins and recovery system, and all of the mechanical and software issues we had along the way. The first part of this project that we tackled was using the BMP280 chip and the I2C protocol to get raw data from the gyroscope. This is the data we would later use to control the servos with PWM.
This code snippet right here shows how we took raw data from the MPU sensor and converted it, scaled it into tilt angle in degrees, and sent it via PWM commands to the servos. We had to adjust these numbers quite a bit once the servos were actually on the rocket.
We then attached servos to a 3D printed motor mount that we designed. After attaching the servos, we tested them by lining the X and Y horizontal axes of the accelerometer up with their corresponding servos and moved the gyroscope and made sure that the servos moved in a way that would correct them given the path of the rocket. And this is a video of that test. After mounting the accelerometer to the rocket itself, we then tilted the body of the rocket to make sure that the fins would move in a direction that would correct the flight path of the rocket. And as you can see in this video, as the rocket tilts to the right or left, the fins will correct and make it keep going straight up. The next step was to implement the MPU 6050 altimeter chip, and we did this by using the I2C protocol to tell the microcontroller at what point the rocket had begun descending. Once a descent was detected or is detected, the microcontroller drives a series of cascading MOSFETs using a GPIO, and these MOSFETs are used to ignite an ejection charge that deploys the recovery system parachutes. We tested to make sure that the altimeter was functioning correctly in conjunction with the microcontroller by attaching it to a small power source and throwing it in the air and making sure that the GPIO is activated using the user LED. From there, we made sure that the MOSFETs were being driven correctly by using the microcontroller user button to make sure that the GPIO was activating them and that current was flowing. We finished this portion of testing by making sure the current would trigger an explosive that would eject the parachute. When originally designing this rocket, we anticipated it would be powered by water, a bottle rocket. But because of issues of electronics not getting wet, we decided to go with a system of solid motor model rocket engines. We decided to place the microcontroller itself higher up in the rocket to give it a higher center of gravity and thus more stability. So we extended the wires that went from the microcontroller to the servos to compensate for this. At the top of the rocket, we attached the nose, which contained the recovery system and explosive to eject it. This section is called the final test, not because this is the only testing we did, because we did many tests that validated the functionality of all the components of this rocket beforehand, but because it would be the compilation of all of the systems together. As you can see, this test was less successful than we had hoped for. Upon reviewing the rocket itself after the launch, we found that only two of the five motors that we had attached ended up going off, resulting in the sideways path, and the force was too great for the fins to overcome. However, if you look closely at the rocket as it hits the ground, you will see that the ejection charge does in fact go off, indicating that the altimeter did work in concert with the microcontroller and that the parachute would have deployed and would have functioned had the rocket been higher up. As you saw in the video and as you can see here, the results of our final test were suboptimal. However, all of the individual components that we designed did work, both in testing and some of them worked on the actual final test.
Yeah, so the implementation of the adjustment of control surfaces according to the tilt of the rocket, that was successful. We were able to get the fins to move in the corrective way we wanted them to. The fins and the PWM implementation was successful. The I2C communication implementation with the accelerometer data was also successful.
Mhm. And another successful aspect of this was the deployment system itself. We were able to get the altimeter to talk with the microcontroller, and we were able to make the microcontroller control a deployment and recovery system. And that worked both in our preliminary testing, as you saw in the video, and it also worked, as you can see here, in final testing. This is the deployed parachute from the rocket. It did deploy on the ground, but this is something that would have worked and did work because of the descent of the rocket.
Yeah, so overall there were many successes in this project. Um, the final launch, just due to propulsion issues, was not what we were hoping for. But in a future implementation of this project, we are very, very confident that all systems would work as expected.